chapter 13, which is on kinetics of particles, and we are moving on to kinetics of planar rigid bodies. Okay, so before we do kinetics, this is sort of getting to the point where we're going to learn about center of mass and moment of inertia. And we'll see how to compute the center of mass and inertia, because that is going to be very important when we solve for forces using F equals ma. Okay, so you guys have seen center of mass before, right? What about moment of inertia? You've done that. You've done, I think, in calculus, right? You double integral or triple integral, no? Where did you see statics? Okay. Did they teach moment of inertia? There's no motion, right? Why would you need moment of inertia? Okay. Okay. So this is like a review then. Never mind. So. Did you have to compute moment of inertia using the double or the triple integral in statics? No? Okay, I wouldn't expect you to do it in this class either. I would expect you to compute moment of inertia and center of mass of composite bodies, which I'll talk about in a bit. So let's review center of mass. So the definition is, it is the location of the total mass of the body, and it's denoted by x bar, y bar, and since we are only doing planar rigid bodies, we are not interested in z bar, okay, but a three-dimensional body would have a z bar too. So the way you compute x bar is you find the mass of individual points on the body, multiply it with the location of the center of mass of those points. In this case, if it's a point, it's going to be just the location of the point. If it is composite bodies like squares, rectangles, it's going to be the center of mass of the square or rectangle, and you divide it by the mass. So this is like a weighted average, right? You weight by the mass to get the center of mass. Similarly, y bar is mi yi divided by the sum of the masses of individual part elements, or the total mass of the body. Okay, and this will be clear when we do problems. Moment of inertia. I'll just define it with a formula. It's really the resistance to rotational motion, just like mass is the resistance to linear motion. So if there's a rigid body and it's rotating about, let's say, the z-axis, this is r, this is a small element dm, then so dm is the mass of a small particle on the body, and in order to find the inertia, what you need to do is take the integral of r square, which is the distance of that particular particle, times dm, which is the small element mass, and then you integrate over the mass of the body. So you've got to take this integral over the entire body in order to find the mass, find the inertia. Okay, so I'm not expecting you to know how to do that integral. However, what I'm expecting you to do is remember some of these things, I might provide the formula. I'll let you know if I'm going to provide the formulas. The formulas are right here. Okay, so this is 8 different bodies of whose inertia you are supposed to know, but turns out that not all of them are really important. Well, all of them are important, but I tell you, some of these come again and again. So the cylinder is important. Usually, the cylinder rolls upon the z-axis. The z-axis is shown here, so that's important. Turns out that the inertia of this is the same as the inertia of the circular disk about the z-axis. So if you think of those two together, then you kind of remember the formula for inertia. It's mr squared divided by 2. Okay. Now an easy case is this. Okay. This is, if you think of the integral r squared dm, the mass is uniformly distributed along the rim. So when you integrate r squared dm, you can actually pull out r square and you'll get integral dm, and the integral of dm is just m. So that's how you get this formula. Okay, so that's super easy. I think the ones which you have to really remember are, well, this mr square divided by 2. This one will show up in the problems. I about z for a plate, and then inertia of a rod. This one. So I think that 1, 2, 3, 4, 5. Oh no, not all. So when I'm saying all of these, I'm not saying that you got to remember these. Don't worry about this one. You just have to remember this formula. Not all the 3. So if I will not expect you to remember all formulas. I can tell you that these 6 I've highlighted here are the most important ones. Those are the ones which you see most of the time problems will be on that, and maybe perhaps this one. Seven formulas. Okay, this is, as I said, easy. Everything is easy. Okay, I'll let you know if I'm going to provide you formulas. Seven. No, there are 8, but there are really 8 times 3, 24 formulas on this page, because each one has a ix, y, and z, and I think you got to remember only 7 out of those 24. Worst case. That's the spirit. Okay, so before we start doing problems, let me tell you about a very useful formula. This is called the parallel axis theorem, and you've probably seen this. So if that is the axis passing through the center of mass, by the way, center of mass is denoted this way. It's a very common way of denoting the center of mass. I don't know why it's like that, but many books will have it like that. This is center of mass. Okay, so the inertia about the center of mass is denoted by Ig. So this is, I'll call the zg axis. Now it could be xg, yg, but let me write it as zg. And then if you want to find the inertia about another axis, okay, which is parallel, so zg is parallel to zo. Okay, provided zo is parallel to zg, you can write IO as IG plus let's say this is the mass of the body is m, and the distance between the two axes is d. Okay, then this is md squared. So the inertia about an axis not passing through the center of mass but parallel to the center of mass axis is given by the inertia of the center of mass plus mass times the distance between the two axes. Okay, and the last thing before we start solving problems is what is known as radius of gyration or gyration, whatever you like to call it. So what happens is many times in the handbooks they will not give you, for example, for a disk they will not tell you the radius of the disk, but they will tell you that the radius of gyration is k. Okay, so many handbooks give the radius of gyration k of a body. In this case, Ig can be found as follows. So Ig is the moment of inertia about the gravity axis. It's simply mass times the radius of gyration k square. Okay, so this is like what they have done is effectively is thought of the body as a ring with all the mass distributed at a radius of k, and the inertia of a ring is mass times r squared. So in this case r is k, and so that's the inertia. Okay, is that clear? Okay, so let's try to apply this on this problem. Okay, so determine the moment of inertia about an axis perpendicular to the page and passing through the pinot, this pinot. The thin plate has a hole in its center. Its thickness is 50 millimeters. So thickness is in the page of the paper, okay? And the material has a density of rho equals 50 kilogram per meter cube. Okay, so when they say inertia about O passing through, it means that the axis is sticking out of, it passes through O, but it's sticking out of the page of the paper. Okay, so if you like, I can draw. It's really hard to draw in. So if this is the, okay, this is the plate, then the axis passes like this. Okay, so I cannot quite show it on a 2D figure. So this axis. So then, how do we solve this? Well, what we can do is, when you have a composite body, two bodies connected together, you can sum the inertias of individual parts. You can also subtract the individual inertia. So for example, in this case, you can think of this composite body consisting of, so this is the body of interest. It consists of the plate without the hole minus the hole. So if you take the inertia of the plate without the hole and subtract it from the inertia of the hole as a solid rigid body, then you would in effect have the inertia of the square plate with the hole. Okay, does that make intuitive sense to you? Okay, so we are asked to find the inertia about O. So I'm going to draw O on all the figures. So let me call this 1 and this 2. So IO12 is equal to IO1 minus IO2. Okay, so all I need to do now is to find IO1 and IO2. Okay, so what is the inertia of a square plate about an axis passing through O? Well, you can find O, but that's not in the table. The table only gives you inertia about the center of mass. The center of mass of the square plate is right in the middle, right here. So let's go and try to find the inertia about the center of mass, and we want to find the inertia about an axis perpendicular to the paper, because if we know that, then we can find inertia about another axis parallel to the axis passing through the center of mass by using the parallel axis theorem. Okay, so I'm going to find IG about the center. So this is a square plate, number 4. Which of these 3 inertias am I interested in? It's X, Y, or Z, right? Which of the IZ, right? Because Z sticks. In this case, the square plate is in the plane of the paper, and Z sticks out. So this one, A and B are the lengths of the plate. So this is the formula I'm interested in. It's 112 mass times sum of the squares of the sides. So if this is A and this is B, then one divided by 12 times mass A, I'll write like this so it's very clear, times A square plus B square. Okay, but that is the inertia about the center of mass. I need to find the inertia about the point O. So since G and O are parallel, I can invoke the parallel axis theorem, which says that the inertia about O1 is inertia about G plus mass of the plate times the distance between G and O. So it's the distance between G and O. So this distance. So my question is, what is that distance in terms of A or B? This is A, so this is B. Well, A and B are the same, so it doesn't really matter. B. What's D? This is 90 degrees. This is going to be 45 and 45. So this distance is going to be, it could be A sine of 45 or B sine of 45. It's the same thing. So A sine A or B is 1.4. So 1.4 times sine 45. So what's 1.4 sine 45? .989. Okay, 0.989. Okay, so I'm going to write it as d squared. That's it. So that's the inertia of the square plate about. So let me fill in the dot. So 1 by 12 times mass. Mass is density. I can write it here. Mass of that is rho times the volume of the square plate. The volume is given by A times B, that's the area, and the thickness is T, so let's call that thickness. So this is A 1.4 times B times thickness, so thickness is 0.05 times 1.4 square plus 1.4 square plus 1.4 times 1.4 times thickness, which is 0.05 times what you just told me, 1.989 square. Oh yeah, I missed the density. Good catch. Let me rewrite this. I miss rho. So rho is 50. Okay, what I'm going to do is, just to make this easier to write, I'm going to pull out the mass. So rho is 50 times 1.4 times 1.4 times 0.05. That's the mass. 1 divided by 12 times 1.4 square plus 1.4 square plus 0.989 square. This is better. So if you do the math on this, it comes out to be 6.4 kg meter square. Okay. Now you've got to find the inertia of the circle. So again, I need to find inertia about the center of mass first, and then find the inertia about rho. So this is effectively a disk, right? You agree it's a disk? So we need to find the inertia of the disk about an axis passing through the center and sticking out of the plane of the disk. And so we go back to the table. This one right here, circular disk. Okay, so which of those inertia should I use? X, Y, there are 4 formulas, X, Y, Z, and Z prime, Y, Z prime, Z prime. Which one? Z prime, Z prime. Z, Z, okay. Z prime can be used if you are interested in inertia about the axis passing through the rim of the disk. In this case, I'm interested about the center of about G, so it's going to be I, Z, Z, and sticking out of the plane of the paper. So it's M times R squared divided by 12. So half mass of circle R square plus the mass of the circle times the distance from O. So the distance from O is D square. Okay, so I need to find the mass. So mass of a circular disk again is going to be it's going to be density times the volume of the disk. The volume can be given by the area times the thickness. So the area of a circular disk is pi r square, and the thickness is T. So this is going to be the mass of the disk. So 50 for the density. I'm going to pull this out when I do the calculation. Pi into the radius. The radius is 0.15 square times the thickness 0.05 times r square 0.15 square divided by 2. So this is r square divided by 2 plus 0.989 square. Okay, is that clear? And so this comes out to be 0.175. Okay, so all that is left is to use this formula here. So 6.4 minus 0.175, that is 6.23.
In the parentheses, there is good one for 0.0989.
0.989, yeah.
No.
This is 0.989 too.
Yeah, but there is where it's coming for that.
Thank you. Okay, is that clear? Okay, now can you think of an alternate way of doing the same problem? I claim that this is not the only way you can solve for inertia. Anybody got an alternate way? Can you say that again?
You can move the axis and you can put it at the very bottom so back in the row. Is that what you're at?
No. You can. What I'm saying is you can solve this. So the way I solved it is, I took the composite body and split it into two, and found the inertia about O for the individual bodies and subtracted things out. I'm saying that you can do it in a totally different way to get the same answer. So the alternate way is, yeah, that's right. Do it as one. So you need to do two steps here. So the alternate way is this thing is okay, but what you need to do is find IG12 is equal to IG1 minus IG2. So I'm trying to find the inertia of 1, 2 about an axis passing through G first. And once I do that, then
will this still work if we don't have the same IG, right? This still work?
this will not work if they don't have the same IG. No, but you'll have to, in that case, I would recommend the first method. This is going to be a problem if you have, that's a good point. If the circle was somewhere else, so that the center of mass of the circle and the center of mass of the square plate were not the same place, then this method will fail. So I O is what we are asked to find, is simply Ig12 plus mass of the composite body times d square. Right? So what I've done here is I first find Ig of the composite body by subtracting individual bodies, and then find IO by using the parallel axis theorem. So in the first case, I used the parallel axis theorem on composite bodies and then did the subtraction. In here, I reversed it. I first found Ig for the composite body and then did the parallel axis theorem. Okay, so let me write this down really quickly. Ig 12 is Ig1. The inertia about G is 1 times 12 mass times a square plus b square minus the inertia about the center of mass for the disk is half m disk times r square. Okay, and I'm going to just write the answer down. It's 1.5987. Then IO12 is IG12, it's 1.5987 plus, now in here I need to find the mass of the composite body. It's not the mass of square plate, not the mass of circle, but the mass of the square plate without the circular disk. Okay, so mass of this, so that is simply the mass of the square plate without the without any hole in it minus so mass of the square plate minus mass of the hole, and so that's going to be rho times A times B times thickness minus rho times the volume of the disk, so it's going to be pi r square times the thickness. So this comes out to be 4.723. So what goes in here is 4.723 times 0.989 square, and if you compute this, you actually get the same answer, 6.23. Okay, so 2 ways of solving this, same answer. You can choose whatever you want. As Anthony, right? Anthony pointed out, if the center of mass G is away, not the center of mass for both is not at the same place, then you cannot use 2, because 2 exploits the fact that you can find you can sum the IGs, right? And you will not be able to do that if the center of mass was Q. So the circular disk was away from the center, exact center of the square plate. Okay, so a problem on center of mass and then find the inertia. So pendulum consists of a 3 kg slender rod. So this is 3 kilogram. And a 5 kg thin plate. So this is 5 kg. Find the location of the center of mass G. So this is unknown. My tablet is having a bad day today. Okay. Okay, so then calculate the moment of inertia of the pendulum about an axis perpendicular to the page and passing through G. So we're going to find the y prime, y dash, or y bar, and then find the inertia about G. Okay, so the way we proceed is, well, first thing is find y bar, right? Now in this case, you got to recognize that there is a slender rod and there is a plate. So those are the two composite bodies of interest. So if you want to find y bar, we need to find the mass of, let me call this A and B. So it's easier to write the formula, or 1 and 2. Let's say 1 and 2. So mass 1 times the center of mass y of 1 plus mass of 2 times center of mass of 2 divided by mass 1 plus mass 2. So the mass of the rod is 3 kilograms. What is the center of mass of the rod? Now, when you find the distance, you got to assume a certain origin, certain axis about which you're going to measure things. So in this case, let's say that they have already given it to you. The axis the zero origin is right here. So you're going to measure from there, and let's assume that the positive axis is downwards. Okay. So then what is y1? Where is the center of mass of the slender rod? Assuming it's uniform, it's 1, right? It's right halfway of 2 meters length of the rod, so it's 1 plus mass of 2, mass of the thin plate, that's 5 kilograms, times where is the center of mass of the plate? It's 2. 2 is the distance here plus this distance. It's half of 0.5, so it's going to be 2 plus 0.25 divided by the total mass of the pendulum, which is mass 1 plus mass 2. That's going to be 3 plus 5. So it turns out that y prime is 1.78 meters. Okay, so if you look at it, the figure, it shows this kind of correctly. It's more than 1 meter. 1 meter is right here, and it's less than 2 meters. So it looks right. Okay, sometimes I might give you a wrong G, and you got to think about it. Unless you calculate, you cannot be sure where G is going to be. So we found y prime. We got to find the inertia about G. Okay, and note that G is the inertia of the composite assembly or the complete pendulum. So what we can do is we can draw the composite pendulum and then split it into two parts, just the slender rod and just the thin plate. So 1, 2, this is 1, this is 2. So IG12 is IG1 plus IG2, right? This is going to be plus, because in this case you just have to add them. You can, in the previous case you subtracted because the plate, the circular thing was removed. So I'm going to now write the inertia of G1. So this is a slender rod. So we need to find the inertia of the slender rod about an axis passing through the plane. So the axis sticks out like this and passes through G. But in the table, there's not going to be an inertia for axis passing a value for the inertia passing through G, as it is shown here. G is not the center of mass of the slender rod. The center of mass is somewhere here, right? It's at 1 meter. while we want to find the inertia about this point. So we have to find the inertia about the center of mass, G, the actual center of mass of the rod, plus m times the distance of this axis from the center of mass. So we have to invoke the parallel axis theorem. Is it clear? So first, find the inertia of the slender rod. We go to the table. This is a slender rod. Inertia is 1 divided by 12 mass times length squared. So 1 divided by 12 mass slender rod length square plus mass times this distance d. Okay, so let's call that d1. So d1 is going to be the distance so it's going to be this distance, right? Or in other words, it's simply y bar minus 1. You agree? Y bar minus 1 square. Okay, because y bar is the distance of this point from the origin, and 1 is the distance of the center of mass from the origin. So the difference between the two will give me this. So that's Ig1 and Ig2. So we need to find the inertia of thin plate. So again, we need to go back to the table. So this is a thin plate. The inertia about an axis passing through G is 1 divided by 12 mass times a squared plus b squared. So go right here. Let's call this A, let's call this B. So it's going to be 1 divided by 12 times mass times a square plus b square plus mass of the thin plate times the distance of the center, which is going to be right here, middle, to G. So this distance is going to be, I claim it to be 2.25 minus y prime, because 2.25 was the distance of the center of the plate from the origin O, and y bar is the distance of the center of the composite thing. So this is G. So this is going to be 2.25 minus y bar square. Okay, m, this is given to be, see, it's 3, mass of thin plate is 5, a equals 1, b equals 0.5, y bar we computed to be 1.78. So all those things on the formula are given. So I can now compute Ig12. The answer is 4.45 kg meter square. Okay. So again, to summarize all these problems, you got to think, what are the simplest blocks I can use in order to find the net center of mass as well as the inertia, and those 7 formulas are important. I'll see you on Friday. There's a quiz. I'll also email the guys who are not in the class.